So, the stuff that you've done so far, or in the last class, you saw EMF, internal resistance are very important points. EMF, internal resistance, and calculations using that, right? So what happens when a cell is connected to an external resistance? What it does is the cell will see its own resistance and external resistance together, and then it will decide how much current to push. So the current that is drawn from a cell depends on the external resistance and also on the internal resistance. Now what happens when a current passes through like that? It creates a potential drop outside and also has a potential drop inside. Now the potential drop inside the cell is of no good use. It's totally useless, but we can't help it. So the smaller the internal resistance, the better for us, because then you have less loss inside. I also did calculations based on power loss, right? How much power is lost inside? How much power is delivered outside? We did those calculations. EI is the power supplied by the cell. I square capital R is the power that is dissipated out in different forms. I square small r is the power that is dissipated inside the cell as what? As heat. So we saw these things, and that makes a big difference. Like if the cell is kind of used already, the internal resistance builds up and therefore becomes less efficient, right? So even though the EMF is 6 volts, what you're getting outside is probably just 4 volts, so the efficiency kind of drops. So the potential difference across a cell is never the EMF. That is what we did. The EMF is E. The potential difference across a cell is never the EMF. It will be either less than the EMF or more than the EMF, depending upon which way the current is flowing. If the current is taken out of the cell, then the potential drop inside is going to be opposite to the EMF. And so if there's an internal resistance here and the current is flowing this way, then you have a potential drop of IR plus minus, and the EMF is plus minus, so it's actually opposite. So the terminal potential difference here is going to be EMF minus IR. This minus this. Whereas if you're having a cell that is being charged, a cell that's being charged is going this way. So the internal resistance is R, the drop is going to be IR, positive this side, negative this side, and this is positive, negative. So what the EMF tells the voltmeter, the EMF tells the voltmeter, I'm positive, and the drop is also saying, I'm also positive. So the V is equal to E plus IR. So this is a situation where the terminal voltage is less than the EMF. This is a situation where the terminal voltage is more than the EMF. And how much lesser is this drop depends on how much current is flowing, right? To give an example, imagine you get into your car, just turn the key once. Okay, turn the key once. What will happen? What do you see? What comes on? The lights, all the dashboard lights and all that comes on, right? Now, remember the brightness of those lights. Now, as the lights are there on the dashboard, turn the headlights on. Just turn the headlights on. What do you see on the dashboard? Why? My question is why now? Can you explain to me clearly as to why the lights of the dashboard dims when you turn on the headlight? Yeah.
They do it on purpose, so that like, if you're driving at night, it's not like
No, it's not a purposeful one. I know no, a purposeful one, you can actually control it. You can control it. It's not purposeful. And yeah, do you know the answers for that? Why does the dashboard light kind of dim when you just turn the headlight? Car engine is off. The engine is off. Yeah.
Does something like the current have to go to the lights, and it has to take away from the dashboard? It's like when you the Kirchoff's rule, the sums have to equal each other, so it's gonna be less than this.
Each one is going to get a share. But look, this is what happens. So let's say this is your car battery, 12 volts, and the internal resistance, let's say, is 0.2 ohms. Just giving a resistance 0.2 ohms. Now, if you connect it to those little lights, this is dashboard lights. All the dashboard lights, how much current is going to draw? A small current. So let's say it draws a current of, the dashboards are going to draw a current of, let's say, 1 ampere. If the dashboards are going to draw 1 ampere current, right? How much is the internal drop? How much is the internal drop? If the current here is 1 ampere, how much is the internal drop? How much? 0.2 volts, plus, minus. So if I connect a voltmeter across here, how much will it read? 11 point? Yes? When you connect a voltmeter across the cell, it will read only 11.8 volts because of this drop. You understand this? This is when you are having only the dashboard lit up and you're not turned the headlights on. Now suppose you turn the headlights on. Suppose you turn the headlights on. Now the headlight probably is going to take a current of, say, 4 amperes. I'm just giving a number. If the headlight is going to draw 4 amperes current, what will be the total current that's going to pass through here now? 5 amperes. So if 5 amperes is going to run through here, how many volts will be dropped? Previously the drop was only 0.2 volts. Now it will be 5 amperes times, which is 1 volt. So the internal drop increases from 0.2 to 1. And what will be happening to the external voltage, the terminal voltage? It will be just going to 11. You see it? The terminal voltage across the battery is only 11, not 11.8. It's lower. That means what? That means that the dashboard lights will receive not 11.8 volts, it will receive only 11 volts. Previously they were receiving 11.8, but now they're receiving, you understand that? It's all because of these lights. If the lights were turned off, it will be bright again because the drop is going to be only, the terminal potential difference will be this. Yeah.
So it has no purpose, the lights dimming, of just like seeing, like, because a brighter light than dark is like, bad.
Oh, that dimming is something different that you can control. Like this can be used, you can use a dimmer and dim it as much as you want. You can dim it very, very, very much, or if you want to see it brighter, you can make it brighter. Making it easier for you to see, that's a different thing. But I'm talking about just in whatever situation the lights, the dashboards are lit, from that position, when you turn on the headlights, it will dim. Right? There's no doubt about it. Yeah.
So why does the voltmeter go from 1.8 volts to?
Because when you turned on the headlights, the current here is like more, right? So the current here is going to be like 5 amperes. If the current is going to be 5 amperes here, how many volts drop it will create inside the cell? The internal drop, the IR, internal drop, that's going to be 1 volt because 5 times 0.2 is 1. So what is the internal drop telling to the voltmeter? I'm -1. And this one says I'm +12. So what happens is the voltmeter only registers 11. Understand? When the voltmeter registers 11, what is that? That is the terminal voltage. That is the terminal voltage. Which means the dashboards and the headlights are now operating on how many volts? Not 12, but 11.0. Before you turned the headlights on, how many volts were coming to the dashboard? 11.8. But when you turned on the headlights, both of them are going to suffer. This is not going to get 11.8s. It will be 11 only. This is what we get for all the devices. Now, If you turn the engine on, if you're starting the car, that's the starter, the starter motor. If you're starting the car, and let's say the starter motor draws 25 amperes. If the starter motor draws 25 amperes, just to start the car, only that starting moment. So when the starter motor is going to draw 25 amperes, what will be the current here? 30 amperes. How many volts will it cause? What will be the potential difference here? Drop 30 times 0.2. 6 volts drop out of 12. So momentarily, the battery voltage will like drop. This voltage here will drop all the way to 6. Only the momentary thing. But if you just keep trying like that all the time, it will finally die. That's why it's a momentary thing. When you start the car, that's why it's recommended, like, don't start it, stop it. Start it and stop it. You know, keep doing this multiple times. What's going to be the consequence? You're using the battery severely, but not waiting for it to charge back again up. You understand? So eventually the battery will fail if you do this many times. If you start it and shut it off, start it and shut it off. If you do this action multiple times, the battery's internal resistance will start growing, and then suddenly there will be a point when this 25 amperes is not supplied by the battery because it's too weak, and then you can't take it. You understand? So recharging is something that's essential. You need to recharge. Again, did it make sense? So when you start the car, have you seen all the lights dimming like really bad? The headlights, everything dims. If your headlight was on when you start the car, the headlight will dim. And it'll dim just for a fraction of a second, but as soon as the car starts, this starter motor, as soon as the car starts, there is an alternator, which is basically a generator, that comes on. Because once the engine starts, the alternator comes on, and once the alternator comes on, battery is being charged. The alternator will charge the battery like this. So what is the alternator going to do? Alternator not only charges the battery, it also supplies the required current for the lights and dashboard and all those things. Of course, starter motor is not going to work anymore. So once the alternator works, starter motor is cut off, and then the current is supplied to the dashboard and current is supplied to the lights, perfectly normal because the alternator is much powerful. And therefore, each of these will get a high amount of share, and therefore it will be bright again. Okay. Make sense? So if I ask you the question, why should the headlights of a car dim when the car is turned on, when the car engine is turned on? You should know. Can you tell me now? Why? Why should the headlights of a car dim when the car is just started? Ignition, yes.
There's an increased current, so when that happens, the internal resistance is higher.
Internal?
Resistance.
Not resistance. Internal
Drop.
drop. Resistance is not going to change suddenly, but the internal drop will change. Okay, so you should say internal drop increases because of the high current. And because of the internal drop is high, the terminal potential difference is low. And that is the reason why the headlights don't get all the 12 volts. It gets only momentarily 6 volts. And that is when you see the headlights kind of almost dying off. But as soon as the engine kicks on, then the alternator is on, the lights come back. In fact, lights are brighter. Lights should be brighter than when your car is on battery alone. Why? Why are the lights brighter? Because when the alternator is working now, the potential difference across here is going to be higher than 12, right? Because the current is going inwards. Therefore, the terminal voltage is going to be like 13, 14 volts. And that means the headlights are getting that much. The headlights will be getting a lot of it. And that is the reason why everything turns brighter. Everything will become brighter. Make sense? Okay. Now, coming back to Kirchoff's laws, I mentioned the two laws clearly. The first one is summation of currents is equal to 0. And the second one is summation of EMF and potential difference is equal to 0. This is true at any junction, and this is true in any closed loop. All right, those are Kirchoff's laws. Now, before you actually start solving problems using Kirchoff's laws, you need to learn about sign conventions. So what is a sign convention? So just pay attention to this. Sign convention for this. Which EMF do you consider to be positive? Which EMF will you consider to be negative? Okay, that's called sign convention. So when you're searching in a circuit, which EMFs will you consider positive? So for that, if there is a cell like this, if there's a cell like that, and if you're searching in this direction, if that's the direction of search, how do you get EMFs and potential? You have to search for it, right? You have to go along a closed loop and search for it. And when you're searching for it, if you're actually searching in this direction, which terminal are you going to hit first? Positive terminal. So because you're going to hit the positive terminal only, then this EMF is positive. You get it? Irrespective of which way the current is flowing, you may have a current going this way, doesn't matter. You don't have to worry about the direction of current. Ignore the direction. When you're searching for the EMFs, ignore the current directions completely. Don't worry which way the currents are going. All your focus must be this one. Searching in this direction, am I hitting the long line first or a short line? That's all your focus is going to be. So now if it is going like this, now if you have a cell like that, you're still searching in that direction. You're looking for it. Which terminal are you going to hit first? The negative terminal, right? So you consider this EMF is negative. You understand this? So these are some of the rules that you're supposed to follow in order to get to proper usage of Kirchoff's laws. All right. Any questions on this? Good. Now we need to know about this. Which potential difference is going to be considered positive and which potential difference will be considered negative. So let's say you're searching in this direction. Let's say you're searching in that direction, and if you are looking at a resistance and if the current is going with you, you're searching in the same direction as the current. In other words, here are the students who are running the race, right? Think of it that way. The students are running the race, they're going through this racetrack, and you are searching in the same direction. So when you search in the same direction, where do they have higher potential? On the left side. So it will be higher here and lower there, correct? Potential difference will be higher here. So which are you hitting first is positive. So this potential difference is positive. So the potential difference across this is positive. And how do you find out the potential difference? How do you find the potential difference V? Yeah. So it will be a positive IR. It will be a positive voltage. Do you get it? Now, after doing all this, you have to keep all this in your head in order to proceed with your work. If you miss any of these conventions, then you're not going to solve the problem. That's why it's very important that you pay attention. Make sure you understood everything about EMF. Good. The next one is searching for the potential difference. This is exactly the rule. Now suppose you're searching in this direction. Suppose you're searching in this direction and the current is coming in that direction. The current is coming against you. So how is the potential, which end of this one is positive, which one is negative? The right side is positive and left side is negative. Now when you're searching this way, which one are you hitting first? Negative. So this potential difference is negative. And so what is V equal to? Negative R. Make sense? Does it make sense? That's it. If you know how to use these conventions properly, you're ready to solve problems. You're ready to solve problems. So we know the conventions that are used for EMFs and potential differences. Now let's go straight into problem solving. And we're going to solve a problem that we already know the answers of. So it'll be easier for you to kind of work with this. Alright? We're going to solve a problem that you already know the answers. So let's start with this. Let's say this is 6 volts and 2 ohms. Alright, can anyone tell me the answer for the current here, right now? Without using Kirchoff's laws, just like look at the board and tell me what is the current right there. Check this. So if you look at the combination of these two, they are in parallel. So 12 times 4 over 12 plus 4 gives you 3. 3, 1 and 2 are all in series, making it 6 ohms. So you should get the current here as 1 ampere. So you already know the answer for this. But we're going to solve the same thing by using Kirchoff's laws. Alright? So for the time being, I'm saying like I don't know this current. So this is your first task. When you're given a circuit where Kirchoff's laws are required to be used, what you need to do first is assignment of currents. You have to put currents down, all algebraically, because you don't know the numbers. So I don't know what current it is, so I'll call it as I. Do you know the current here? I. Do you know the current over here? Call it I1. Because you don't know what it is, call it I1. What is the current here? I minus I1. Good. So don't use too many variables. Try to simplify it as much as you can. What law have you used to get this number here? I minus I1. What did you use? The first law, which says net current is equal to 0 at any junction. So this is your junction. You know the incoming current is I. Some of it is going this way, so the rest has to go this way. That is the first law of Kirchoff. You're using it. And if you don't use the first law, then you'll call it I2. So you know how many variables will be there then? 3 variables. So you're going to create more trouble. Minimize the number of variables. So the first law is used here. So what's the current here? It is I minus I1. And the current goes, see, it's a good idea to keep putting those arrows wherever, because it's very important. Now this is the current going here, that's I1. And both these currents are going to join together and form I. That's your first task. Before solving a problem, that's your first task. Putting current assignments. We have done that by using Kirchoff's first law. Now it comes to second one. Second law. Before you do the second law, you need to use loops. How many loops are here in this? How many loops are here? 2? 3 loops. Look, this is one closed loop. This is another closed loop. You don't have to have the cell. It's a closed loop. And then this whole thing is another closed loop. So we have 3 loops. But how many loops do you actually need? How many variables are there? If you have only 2 variables, you just need 2 loops. You don't have to use all the loops. If you have 3 variables, then you need 3 loops minimum. You cannot get the answers by 2 loops. Okay? Now, that's why it is a good idea to minimize the number of variables. So how many variables here? 2. Therefore, you just need to work with only 2 loops. Which loops are you going to work with? I'm going to work with this loop first and this loop next. And in both cases, I'm going to go clockwise. When I do the job, I always go clockwise. So I'll just make it a point. Okay, I'm always searching clockwise, which means I start from here and I go clockwise. I start from here and I go clockwise. You know, just to make it a pattern. So you don't have to confuse yourself at some other time saying, oh, did I go this way or this way? You know what I'm saying? You're free to do any way you want. I've seen some students going clockwise here and then counterclockwise here and mixing it up. And if you do that, the problem is suddenly you will forget which way you were searching and then you will get a wrong number. And one little wrong number is enough. That's enough. You get totally wrong answers. Although you use Kirchoff's laws everywhere, one tiny mistake, a plus to a minus, that's enough. So I'm going to go clockwise and make it a habit to go clockwise every time. And all right, this is my first loop. I'm going to start from the left-hand top corner. That's what I always do. For any loop, I'll start from there. First time, so I'm going to make 2 searches. I'm going to look around for only EMFs. That'll be my first search. So if I'm going to go around the circuit, I just go around. Okay, I want to see where is the EMF. My focus is only on EMF. And I come back. So I've searched for EMF now. Now let me do my second search for the other ones. Like imagine if there are boys and girls seated there, like many different boys and girls seated, and you're given the job of, okay, count how many boys and girls are there. It'll be a good idea to kind of go searching for only the boys first. Come back. Now go and search only for the girls. Come back. That'll be better. Instead of like, okay, I met 2 boys and 3 girls. Confusion of both of them together will be there, right? So what you can do over here, start from here, search only for the EMFs. You know the rules for searching for EMFs. I'm going to search clockwise for EMFs. Tell me, as soon as you touch the first EMF, tell me this. How much it is? Positive or negative? Positive. Why? Because you hit the long line first. Simple. Right, Nick? You're hitting the first line. You're touching the positive line. That means because it's positive here, negative here, you're going to call that +6. So my equation for the first loop is going to be +6. And I keep searching for it. For what? EMFs. I'm looking for EMFs. I don't find any more. I'm back to my starting point. Now what do? Start my second search. This time I'm searching for potential drops. Tell me as soon as you come across a potential drop. Is there a potential drop here? Positive or negative? Why negative? Because you're going against the current. Simple. You're going against it. You're searching this way and the current is coming in the opposite direction. So what do you call this potential difference? How much is it? Negative? 1 times I. So which is? You get it? So it's IR. It's actually IR, but it's negative. Tell me the next time you come across a potential drop. Tell me if there is a potential drop anywhere. Is there a potential drop here? Yes. How much? Negative? 2 I. Yeah, 2 is the resistance and I is the current coming in the opposite direction. So it's negative 2I. Keep searching. How much? Positive? You're searching this way. It's still negative. Alright, negative what? 12? I1. The current is different now. The current is different. Through the 12 ohms, the current is not I. It's I1. So it's negative 12 I1. And I'm back. And Kirchoff's second law says all this must be equal to 0. So what you do now is to kind of simplify that a little bit and make it into a decent equation. So how do you simplify this? 6 minus 3i minus 12i1 is equal to 0. So I can write it as 3i1 plus 12i1 ups 3i plus 12i1 equal to 6. Right? Is that okay? Yeah. Now divide throughout by 3. I can simplify it further. So I plus 4i1 equal to 2. So this is my equation number 1. I'll keep it aside. Leave that out. Now you need to go and tackle the second loop. So I'm going to the second loop. This is my second loop. Just this. If I start from here, tell me EMFs. Did you meet any cell? Nothing. So 0. Didn't meet anything. Now start your next search, which is potential. So alright, how much is the potential difference here? 12? I1. Positive, negative. You get it, Chris? You seem to be lost.
No, okay. How did we get to 0?
Because from here back to here, did you see any cell? So, this is it. Okay?
How do you decide when it's positive or negative?
That's why I gave the rules earlier. What did I say about the rules? For the cell, the positive is when you hit the positive side first.
Yeah, I get the cell.
For the resistance, you look for the potential drop. When a current is going this way, which side is positive potential? Left or right? Left is plus and minus. Now when I'm searching this way from here, I'm hitting which one first?
Positive.
So that's positive. So 0 plus 12i1. Yeah, ask me questions if you cannot understand why I wrote plus, why not minus. Yeah.
When we were doing those rules, like which we were searching, if we were coming that way on like the resistance, you said that like the plus was on the right and the minus is on the left. I guess
If the
we're-
current was coming this way,
yeah, so
yeah,
then
then it'll be
why-
plus here, minus here.
So then why is that one?
Here the current is going in this direction.
No, I'm saying like if in the other situation, why is it negative? Like why is
And the other loop, it was negative.
It's the one that you
Oh, it depends on your search direction. In this loop, you're searching this way, so you ended up crossing from this side. But for this loop, you're searching this way, so you're going the opposite direction. Remember that.
So would it be a good idea to put the positive and like draw the positive and negative on each side?
Yes.
That's what-
It'll be a good idea. It'll be a good idea to put plus and minus so that you will be alert about it. That's a good suggestion. Yes.
like in the when we were searching from the right and going to the left, it had like the plus on the right side and the minus on the left side. So, but I thought it was
Say it once again. Say it once again.
like when we're searching. Oh, actually, never mind. I
You
get
got
it
it?
now. I get it. Yeah.
Got it. Okay, good. So for this one again, there are no EMFs all the way here. Now for the potential drops, you are searching in this direction. You're searching clockwise. So you went this way. So since you're hitting the plus first, it's plus 12i1. And then now you keep going. Keep going till you hit the next one. What is that? Negative 4. Negative 4i minus i1. Understand why it's negative? Because the potential is like plus minus. So that's why it's minus. And the current is I minus I1. So you do that. Came back here. Your job is done. Equal to 0. Now simplify this and make it neat. So what's happening here is 12. Okay, so 12i1 minus 4i plus 4i1 equal to 0. So this makes it, here we go. So 16 minus 4i plus 16i1 equal to 0. Is that right? So if you divide throughout by 4, you can get, if you divide by negative 4, you can get I minus 4i1 is equal to 0. Let me know if you don't understand something. I divided throughout by minus 4. So I got this. That's my second equation. Once you get these two equations, just solve it. simultaneously. You know simultaneous equations. Just solve it. How do you solve this? Add them. So it depends. Like, see here I can add them because this is plus 4i1 and this is minus 4i1. So if I add this equation, this gets knocked out. So if I add 1 and 2, what do you end up getting? So I plus 4i1 equal to 2 and I minus 4i1 is equal to 0. If you add both of them, I get 2i is equal to 2. So I is equal to? You got it. The current is 1 ampere. So we discover the current. Oh, we already know the answer is 1, but by this method, we are getting it right there. So if there's a situation where you cannot use your Ohm's law and all that, how do you simplify it? This is exactly what you do. You get it? Now that's not the end of the story. This is I. Can you tell me how much is I1? So just pick it up and put it there. So put this I here and solve for I1. If I is 1 ampere, so 1 minus 4I1 is equal to 0. So what is I1? 1 over? So this current is 1 over 4 amperes. You're just solving it and getting the answer. You're not using anything else. Now how much is this current? So that is 1 over 4. So it's 1 minus 1 over 4, so 3/4. So you discover I and I. So basically you got all the three currents. I is 1 ampere. I1 is 1/4 of an ampere. And the other current, I minus I1 is equal to 3/4 of an ampere. Any questions on the use of Kirchoff's laws? Are you ready to tackle a complicated one?
Let's do it.
Yes? Alright, this is your new sum, new problem. The circuit stays, everything stays the same, but there is an additional cell here, which is 5 and 1 ohm internal resistance inserted. Now, can this be done without the help of Kirchoff's laws? No. Because there are more cells. It's not easy to work with this circuit absolutely by using just Ohm's law. You have to go by Kirchoff's laws. So I'll give you some time, but before I give you the time, let me do the first part of it, which is current assignment, so that everyone will be on the same board. Okay? I'll call this current I, just like before. And so I is coming here. And remember last time we called this one as I1? Yeah, you can call this as I1, and that will be I minus I1. It's up to you. You can call anything you want. So I and I minus I1. So for uniformity's sake, I am assigning the current directions for you. Now, remember one more thing. These are your guesses. You're guessing that the current is going this way. Will the current actually go that way or not? Your final answer will tell. You understand?
Oh, so like if your final answer is negative, it means
That means this was not going this way, but it's going the other way around. That's what it simply means. But you don't have to worry about it. You just go by guesses. All right, you're just guessing. This current definitely is not going to go that way. It's going to go this way. That's a educated guess. But this one, it could be. See, look at the cell. It could go this way or that way. Don't know. Doesn't matter. Just guess it. Guess it. The first part is just guessing. And there's nothing wrong in guessing the current direction wrong. Why? Because your answer will tell whether you're right or wrong. All you do is, okay, if it is not 1/4 this way, then it is, if it is negative, then it's going to be this way. That's all. Switch it. So I'll give you some time. You can work on loops 1 and 2, because only 2 loops are necessary, and get the answer. Let's go for the solution for this one. So I'm going to start from this corner for that loop. And as I said again, be more systematic instead of like jumping around and searching for the values. If you're systematic, you will get beautiful equations. If you're trying to jump around and couple things together in a faster manner, there's a chance you miss something. Okay? So if you're going from here, first my search is EMFs. As I said earlier, I'm searching for EMFs. That's +6, that's -5, and back to 0. So 6 minus 5. Then now the potential drops. that's minus I, and that's minus 2I, and then this is going to be, the current is I1, and I'm going against it, so this is negative I1, and that will be negative 12I1, and back again, equal to 0. If you've got that equation right on your back. 1 minus, this is 3I minus 13I1 is equal to 0. If you simplify this equation, 3I1, 3I plus 13I1 is equal to 1. Is that equation okay so far, everyone? Yes.
How'd you get negative I1 along with negative 12I1?
Because
I
both,
see how you get 12I1.
yeah, why is it negative?
That's the. Is the
Yeah.
is the cells always negative I?
Mhm.
Is the cells internal resistance always?
No. Depends which way you're searching. If you're searching like this, it's positive.
On the top one, are you searching?
I'm searching clockwise.
Yeah, but on the top, what is it negative? Oh wait, yeah, never mind.
That's negative I. And that's negative 2I, same current.
Okay.
But when it comes here, it is negative I1 because it is a different current. That's why it's a good idea to mark the currents everywhere. Mark the variable everywhere. So you will immediately bump into it. Instead of marking the current here, you'll be like tempted to think that it is still I. Right? So the rule is this: as soon as you go to a junction, the current is going to change. You can't just continue doing the same thing. Yes.
Wait, so for the 2 ohms in the cell, why is that negative?
For what? For which one?
Why is it negative to I?
Because you're searching in this direction, which is against the current direction. Which way is the current here? This is I going in this direction. Which way are you searching?
Okay, so it popped up.
So it all depends on search. If the search is with the current, it's positive. If the search is against the current, it's negative. Right? If you're searching with the flow, then that's positive. Leave that there. Now let's go to the second loop, starting from here. I'm searching for the EMFs first, so that's 5 and nothing more. So you have 5. Now going to the currents, potential drops. The first potential drop is 12I1. This time it's positive because my search is in this direction and the current is assumed to be going in the same direction. So that's positive. Next resistance I'm meeting is this one, which is plus I1. Because why? I1 times 1 is plus I1. Go searching. Now, see, the current has changed. This current is I minus I1, remember that. The current is here different. So when you come here, this is going to be a negative drop. So negative 4 I minus I1. And back. Equal to 0. Simplify this one, 5 plus 12I1 plus I1 minus 4I plus 4I1 equal to 0. And so it's 5, 12I1 plus I1, 13I1 plus this, so 17I1. And I is this 4I. So this becomes 17I1 minus 4I1 is equal to negative 5. Or 4I1 minus 17I, 4I, 4I minus 17I1 is equal to 5. So we have two equations. One is 3I plus 13I1 is equal to 1. The other one is this. Now what you can do to put them together, multiply this equation with 3. If you multiply this equation with 4 and this equation with 3, the end result is this. The end result is 12I plus 52I1 is equal to 4. That is this equation. and this equation becomes 12I minus 51I1 is equal to 15. Now you can subtract. If you subtract this, you're going to subtract. So this sign changes to plus, this sign changes to minus. So you subtract 12 minus 12, 0. 52I1 plus 51I1 is 103I1 is equal to 4 minus 15 is minus 11. Did anyone get so far okay? Good? Good. And therefore I1 is equal to negative 11 over 103. You can get in decimals. Tell me the decimal answer.
Negative 0.1.
Negative?
Negative 0.1067. It's like 0.107.
Negative 0.107. Substitute this into any of those equations and you get the other values. Now, I1 is coming negative. What does it imply? That means that my assumption was wrong. It is actually going this way. Okay? So, when you see that the current is coming out negative, I1 is in this direction, which means that the assumption was wrong, but it doesn't matter. We understand the actual current is flowing in this direction. So what you do now is substitute that I1 into one of the basic equations. So let's say 3I plus 13I1 is equal to 1. So 3I plus 13 into negative 0.107 is equal to 1. So that becomes 3I minus 0.107 times 13, 0.107 times 13, 1.391 is equal to 1. So 3I is equal to 1 plus 1.391. So I is equal to 2.391 over 3, which is 0.797 amperes. Now that is coming out positive, so that is correct. So the current is in this direction, which is 0.797 amperes, and the current is in this direction, which is 0.107. And then if you want to find this, so we have I minus I1, which is 0.797 minus of minus 1.107. So that is going to be 0.904. So the current here is positive. That means it's correct. 0.904 in that same direction. Only here we have to switch the direction. So it makes sense here. 0.979 coming here, 0.107 coming here. Together it is going to be this. So that is exactly how we solve Kirchoff's laws problems.